small signal stability. When there is a small disturbance on a power system, how the system remains stable and what is the impact on its rotor angle and the frequency of a machine. So now we will calculate and assess all these parameters using this numerical problem. So first of all, what is the statement of this problem? We have a 60 hertz synchronous generator having inertia constant H is equal to 9.94 megajoules per MVA and a transient reactance XT dash is equal to zero point 0.3 per unit. Here, here we have transient reactance of a generator is connected to infinite bus. This is infinite bus 1 through a transformer with a reactance of zero point 0.2. Reactances are marked on per unit. The generator is delivering real power of, this generator is delivering a real power of 0.6 per unit at a power factor of 0.8 lagging uh, to the infinite bus at a voltage of 1 per unit. So a infinite bus has a voltage V is equal to 1 per unit. Assume per unit damping factor at coefficient D is equal to 0.138. Consider a small disturbance delta is equal to 10 degree, which is equal to 0.175 radians. And this is happen when, for example, the breakers open and then quickly close. So this disturbance occur in an instant when a breaker suddenly opens. Uh, it basically causes a disturbance in the angle, which is delta sigma or delta delta, and that disturbance is equal to 10 degree. And after some time, suddenly it closes. Obtain equations describing the motion of the rotor. So due to this fault or disturbance, now we have to write down the equations which actually defines or explains the motion of the rotor and the generator frequency during this instant. So I hope the statement is clear to you. These are the two things, I mean, the motion of the rotor angle and the generator frequency. So we have to obtain those equations. So which are these two equations? Basically, those explaining these both items. I mean, one is this equation, which is delta is equal to delta naught initial angle plus the change in angle, and the change, the disturbance is dependent on the damping ratios and the damping frequency of a system. So by incorporating all these parameters, we will get the exact value of delta. And secondly, we need to have the frequency of a generator. So omega is basically the angular speed or angular frequency. So from here we can have the value of omega, or if we want to write it in the form of f, so we can have 2 pi common from here, and that will again, this equation will automatically convert into f, just like here. So we have to find out this angle delta and omega in this problem. So to find out these values, we need the value of delta naught, omega naught, and then we need to have the value of delta delta naught, zeta, omega and t, omega dt. Similarly here, omega d, delta naught, omega n. So no, we need all these values to find out the value of delta and omega. So in this problem, first we will find out these values so that we can get the values of these delta and omega. Here we have omega dt because we are now finding out the value of f. So instead of omega dt, we will calculate fd. Similarly, instead of omega naught, we will calculate the value of f naught. And similarly, we will find out the value of omega. Instead of omega, we will use fn. So these are the values that we need to calculate in the whole problem. So we will solve the problem in a way that we have to calculate all these parameters. And why we are calculating all these parameters? Because we need to calculate the delta and omega. So starting with the data we have given with, we are given, for example, the single line diagram. First, we need to find out the transfer reactance. In this case, the transfer reactance can be simply find out by having the equivalent impedance of the circuit diagram, which is equal to xt dash plus xt plus the equivalent impedance of these two lines, as these two lines are parallel with each other. So we will solve them in parallel. So ultimately we get the value of x is equal to 0.65. Now, then at the second step, we need the value of s. Why we need the value of s? We need the value of s because we need to calculate the I. And why we need to calculate the I? We need to calculate the I because we need to calculate the E dash. So s will determine I and I will determine E, and E is dependent on I and x. So therefore, we need both x and I. We have already the value of V. From where we can get the value of x? We can get the value of x from the transfer reactors of a circuit diagram, which is around 0.65 in this case here. And now we have to calculate the value of I. Now I is equal to s conjugate divided by v conjugate. We don't have the value of s in this the problem statement, but we have the value of active power 0.6, and we have the value of power factor, which is 0.8. So we know that s is equal to P, which is the active power, divided by P divided by cos theta, cos of theta. So this is the value of S. So we have the value of P is equal to 0.6 in problem, cos is equal to 0.8. So 0.6 divided by 0.8. Then we will have to multiply this with the angle as well. So what is the value of angle? How can we find out the value of angle? So the angle is basically theta, and theta is equal to cos inverse of 0.8. So basically S is equal to, you know that S is equal to S modulus of S into theta, modulus of S into theta. So this S modulus is equal to P over cos, S modulus is equal to P over cos, and theta is equal to cos inverse of 0.8. So that's why we have utilized this formula to find out the value of S. Now we have the value of S here. We will use this in the equation I. So here is the equation of I. We will take the value of S as S conjugate, and because of that conjugate, this angle becomes negative. V, we have 1.0. It will conjugate have little impact on 0. So therefore, the equation will become like this. And this will ultimately lead us to calculation of I. So now we have the value of X and I, and these values of X and I will help us in calculating the E dash, and we will have the value of E dash is equal to 1.35 at the angle of 16.79 degree. So this 16.79 degree is basically the initial operating angle of a rotor. So thus the initial operating power angle, or the angle between the rotor field and the synchronously rotating magnetic field, is 16.79 degree, which is equal to 0.2931 in radians. So using this value of 16.79 degree, we will calculate PS, which is the synchronizing coefficient. And you know that synchronizing coefficient is basically the rate of change of uh, electrical power due to the change in the mechanical power. So the PS is basically the rate of change of the electrical power in a power system in case of any fault. So PS is equal to, and why again we are interested in finding out the PS? Because PS will help us in calculating omega n and zeta. And again, why we are interested in calculating omega and zeta? Because both of these equations will be used in the delta and omega, or the frequency, this formula. So first, PS is equal to P max cos delta naught. This you know from our small signal stability derivation lecture, that PS is equal to P max cos delta naught. Simply put the values in this formula, we will have the value of PS is equal to 1.9884. So by putting us this value of PS in the equation of omega n, which is equal to pi f naught over h, again we obtain this value of pi f naught over h from small signal stability lecture. You can visit that lecture and find out how we have obtained the value of omega n there. So by just putting the value of PS, pi f naught, and h in this equation, we will get the value of omega n. And similarly for zeta, we use the formula d by 2 pi f naught over hps, and the value of d is obtained from the problem as it is mentioned in the problem as well. So now we have the value of omega n and zeta both. As we have the value of omega and zeta both, Now we'll use the linearized second order differential equation, and we will formulate it in the standard form. The standard order differential equation, second order differential equation, is usually written in the form of d square delta delta by dt square plus 2 zeta omega n d delta by dt plus omega n squared delta is equal to 0. So this part will remain just like that. Zeta, we have the value of zeta omega n. Just putting this value of zeta and omega n here and multiplying them with 2, it will become 2.62. And we have the value of omega n again here. Just taking the derivative, sorry, the square of omega n, it will become 37.7. So the linear second order, linearized second order differential equation is written in this form. Again, we have to find out the value of omega d, and why we are interested in finding out the damped angular frequency, because the damped angular frequency omega d will use in this formula here. So therefore, we need the value of damped angular frequency. And what is damped angular frequency? The damped angular frequency is basically the frequency of a transients at a rate at which they are basically dissipating or mitigating in the system. Because of that disturbance, there comes transients in the system. So after the disturbance is removed from the system, or the system basically isolate that faulty area, then after some time these transients starts reducing, or basically started to decay. The frequency at which these transients decay is basically known as the damping frequency, and we are interested in the damping frequency because higher the value of the damping frequency, faster our system will become in the steady state. So therefore, we are interested in finding out the value of damping frequency. So how the damping frequency is different from natural frequency? The natural frequency does not consider the effect of zeta or damping ratio or different inertial parameters of the system. However, the damping frequency take into consideration all these factors. Therefore, the damping frequency or the frequency is the value of damping frequency is usually lesser than the value of the natural frequency, because it takes all the damping ratios and other resistive parameters in consideration as well. So this is damping frequency. Hope it is clear to you if I have not explained in the lecture as well. So I am explaining here it again. So omega d is equal to, that 60 radians per second. So this is the angular damping frequency corresponding to damping oscillation. If we want to know the frequency in terms of frequency, so damped angular frequency of oscillation is equal to radian per second. And if we want to have this term in terms of frequency hertz, so it will become equal to fd is equal to 6 omega d. You know that omega d is equal to omega d is equal to 2 pi fd, 2 pi fd. So if we want to have the value of frequency from angular speed, so the frequency is equal to omega d over 2 pi. So we have used the same formula here. Omega d is divided by 2 pi. So it becomes 0.9549 hertz. So at this frequency, our transients or ripples are basically decaying after the disturbance in this case. So we are actually interested in finding out the value of angle delta and omega. And because the angle delta is basically the motion of the rotor relative to the synchronously revolving field and in degrees, and frequency excursion in hertz are given by f. So frequency excursions, what are the frequency excursions? That how fast your frequency is basically changing during the transient period. So these are the basically known as the frequency equations. So these both parameters are important, extremely important in finding out the stability and of a system. So therefore, now we have all the values of omega n, omega d, zeta as well, and we have the value of delta, sigma, delta naught as well. So putting all these values in both these formulas, we will get the value of delta and f. So now if we want to have the exact value of delta, we will only need to put the value of t here. Whatever the time we actually want to calculate the value of the delta, we will obtain the value of delta at that time. And similarly for the frequency, both of these parameters are dynamic, both of these parameters are time dependent. Therefore, we are not giving their exact value because they will change with the change in time. So whatever the value of the time we will put here in delta and f, so the value of delta and f will change during the transient. I hope this problem is clear to you, and through this problem, the small signal stability and how the rotor dynamics and frequency changes during the problem as well. So if there is any problem, students, you can ask me in the contact on the comment section of this lecture. I hope all the things are clear to you. Thank you very